Greetings to all. Title of my presentation is Charge Transport in Molecular Semiconductors, a Classical and Quantum Perspectives. My presentation consists of three parts. First, I am going to describe the basic concepts of charge transport theories and recent developments on molecular transport material and molecular transport at different physical domains. So next, I'm going to explain about the charge transport in molecular solids in the two way. One is validity and limitations of Planck-Rankin principle. Actually, in molecular solids under the category of matter systems, so large degrees of freedom is there. So this large stretching and bending vibration makes the breaks in the Planck-Rankin principle, breakdown of Planck-Rankin principle, which leads to the non-quantum principle. So due to the non-quantum principle, the energy, electron energy will be hoping will be the each localized site. The hoping site will be dispersive nature. So how the electron and hole, while the electron hole jumping from one side to next side, how the energy loss will be there in the extended molecular system, which is I'm going to explain in that round. Next, I will show the test examples, some important conclusions and observations. I'm going to show. So actually, molecular electronics advantage of molecular electronics is a more flexible nature, environmentally free, easy to synthesis, and one can easily tune the electronic properties via the force substitutions. If you substitute the heteroatoms in the port part, you can easily tune the energy levels, that is HOMO or LUMO energy levels. Accordingly, the electronic properties also changes happen. So next, if you add the side chain in the end substitution, at which the phase property and orientational property, that is self-aggregation property, will change. So this is the main advantage. So easily you can tune the both phase property, whether the solid phase or liquid crystalline phase, like that. According to stability and properties also change, and also one can easily tune the electronic property via the energy level tuning by the appropriate doping in the in the core molecular core area region of the molecular systems. Here, uh, five-step system, we expect the overlap between one molecule to next molecule or within the molecule. So the pi-pi interaction makes you the strong hopping path, which helps to the charge propagation along the uh, stacked molecular system. So application point of view is the molecular electronic devices. So single electron devices or double electron devices can fabricate accordingly. This is molecular electronics and a specific FET or organic field effect transistor and photovoltaic cells and light emitting diodes. These are various optoelectronic application one can achieve through molecular devices. So next is actually in molecular transport theories for based on the intrinsic nature, how the charge is localized, whether it's localized or delocalized in the molecular systems. So normally molecular systems are under the category of soft matters, condensed matter. So large degrees of freedom is there. That is stretching, bending, and various vibrational mode, rotation, free rotation, like that. So which leads the symmetry broken, energy level. That symmetry is broken because due to the structural fluctuations. This structural fluctuation causes the symmetry broken, which leads to the uh, formation of disorder. So at which the electron form, that is mean electron nuclear dynamics interaction between electron and nuclear coordinates will be differ from the inorganic materials. So, based on how much the structural fluctuation and nuclear dynamics is there, accordingly, the electron interact with the uh, that is atomic coordinates of molecular systems. So here, due to that scattering as well as disorder formation, non-resonating effect is there. Non-resonating effect because resonance means uniform interaction. Here we get structural fluctuation is there. That's why we expect a non-resonating effect in the potential energy surface of the molecular solids, which leads to the symmetry break-in. That symmetry break-in and the disorder effect. The combination of these two uh, passes the potential energy barrier in the potential energy profile. So we cannot expect the periodic energy function. So only here we expect the that non-periodic, that is an asymmetry-based non-periodic energy profile, in which the charge, that is electron or hole, will be there. That wave function of electron or hole will be there, localized in particular sites. So if you look the energy profile of the molecular solids, if you look in left side, the energy profile and existence of localization and delocalization both are now one can compare from this figure. So first one, due to the disorder conditions, potential energy surface is many local minima is there. So many local minima is not a same energy line. So in which the each local minima acts as one energy site. So the energy site it has different energy levels. So it leads to the non-periodicity due to the disorder and asymmetric interaction of within the molecular solids. At the same time, if you look the inorganic material, the periodic material, the energy states are will be uh, the symmetric nature. So periodicity is there. So we can look the materials will be there follows the block wave function. So here charge will be there delocalized and within the energy levels. That is continuum energy band. So first one is related with the common room temperature molecular solids. The second one is commonly related associated with uh, the material system, that is quantum materials. So now, if you look at this diagram, we can explicitly we can extract the information from this one. The first left side describe the periodic potential. If you look the potential energy surface is a periodic nature. So same or local minima are same and the maximum also same point. So different same continuum energy band, that is replication, same energy band will be there. So at the same time, if you look on the right side, different local minima is there, energy band, because of due to uh, the structural disorder. So the conformational disorder leads to the different local minima in the potential energy surface. So first case, electronic coupling is larger than vibranic coupling, that is. So that's why all electronic states are interact with each other. Even if you disturb one electronic state, that disturbance, that is perturbation, influence other extended other electronic states also. That means electronic coupling interaction is more. So if you give the one information immediately, you will observe within fraction of second when you can observe other electronic state in the periodic system. So here electronic coupling is large rather than the vibranic coupling value. So here super exchange delocalization transport we can expect. So in this way, all local minimum potential energy surfaces are merged. That means superposition of all localized states are. That means localized means individual energy states are very strongly interaction because electronic coupling is larger. That's why all energy states are merged by the principle of the superposition of all electronic states. Here, continuum energy states are otherwise we can call it as band formation. There is no barrier for charge delocalization. That means here charge transport is kinetically favored rather than that of potential one. Here kinetic terms is dominant. So here charge is more kinetic. So this kind of material more influence the helps charge transport property. That means FET characteristic and photovoltaic and so on. So next one is electronic coupling. Other way you can say in disorder system, vibronic coupling is larger than the electronic coupling. So here electronic states are independent. So each states have different energy levels and the independent one because it's not merged one. Separate states will be existing. So in this way, diffusion is expected. Diffusion limited random. We can calculate the diffusion phenomena through random walk technique rather than other effective mass approach approximation. First case in electronic coupling larger value, that concept is follows the large polaron theory. Second one is a small polaron theory because here vibronic coupling is dominant factor rather than the electronic coupling, in which the diffusion is a dominant factor. Here, many local minima in potential energy surfaces observed in these molecular disorder solids. So here, so in this way, so for many disorder molecular systems, we can calculate the Hobbing phenomena is required. Hobbing means jumping from one localized state to next localized state. So two kind of ways there. One is non-polaric states and polaric states. So polaric information is very important to predict the exact transport property. That means the information about the lattice deformation as well as electron. The combination of lattice deformation and electron is called as a Polaron effect. Polaron is nothing but as an electron when it's localized to the energetic disorder system. So we can say we can define as a when an electron is energetically relaxed in the distorted uh, molecular system, that related electron is called as to be the referred as a proton. So common nuclear proton Hobbing is calculated based on the two way of theory. One is Marcus theory, and another one will be the hydrogen molecular ion theory. Marcus theory is inelastic. Another is a hydrogen molecular theory is called the elastic type. Inelastic type means the scattering will be takes place. The scattering means at each Hobbing steps the energy loss will be there, reappear. That means incoherent transport. And if you take the extended molecular system, one molecule to next like that, the Hobbing takes place. So each Hobbing, the kinetic energy loss will be takes place due to the disorder phenomenon. So, so it can be approximated as an inelastic term. So, so in this way, Marcus theory is combination of any charge transfer theory. We should know three basic concepts. One is the Fermi-Golden rule. Another one will be the density of states. Another one will be the Planck-Random principle. The Fermi-Golden rule describes the how much quick time it takes place from one localized site to next continuum states. So one localized to next reaching state will be the continuum energy band states. So this is the how much quickly time evolution if one can calculate the transition rate of transition probability. This is calculated by the Fermi-Golden rule. Another one is density of states. From density of states, one can uh, obtain the charge distribution phenomenon. How much charge is distributed means localized or delocalized nature, one can calculate. So density of states we already know the density is number of electronic states per volume per quantized energy per within unit energy per quantized volume. Next one is a Frank-Hunter principle. It's a Frank-Hunter principle is commonly the weightage of thermally populated density of states. So based on these three factors, the charge transfer rate one can calculate it. Here, Marcus theory of charge transfer rate is one of the good relation rate equation to predict the two-state model, to predict the charge hopping from one diamond system within diamond. That means charge hopping from one molecule to next molecule. Next, actually, if you want to know the charge carrier dynamics in the molecular solid, we should know the both effect. That means quantum picture and classical picture. Quantum picture means we should know the orbital nature. That means electronic structure, behavior. That means how within the molecule, how the electronic distribution, the HOMO, LOMO levels, the distribution is there. That one we should know. Another one is about the molecular vibration with respect to the environmental effect. That means especially in temperature effect. The nuclear, that is structural fluctuations that which can be based on the temperature, thermal energy. So molecular vibration. So combination of electron in the within the molecules. So we should know aware of two things. We should know the two things. One is quantum picture and classical picture. Quantum picture about describe about the electronic structure of the particular molecular solids. Another one classical picture means structural fluctuation with respect to the thermal energy. So here, actually, from the structural fluctuation, the orientation confirmation one can calculate. This based on the combination of these two, only one can calculate the exact charge transport properties. So commonly, if you look charge transport in molecular solids, if you look here, self-assembly. So if you look any molecules, how the molecules are assembled, structural that is pi conjugated or pi stacked molecule system. This diagram is one of the examples for pi stacked molecule system. With the internal stacking distance approximately in various experimental observation and theoretical observation, one can, we can say it's approximately 3.4 to 3.6 Armstrong in this level. So here at different orientation, conformation disorder also there. So this conformation disorder is based on the structural oriented. That means stacking angle distribution as well as intermolecular distance. In both aspects, we can estimate the conformation disorder. So here basically, for molecular transport, the energy operator we have to operate from the Hamiltonian. Here we are using the type bending Hamiltonian. In the type bending Hamiltonian, two factors. The left part, first part is describe the site energy. Another one is the electronic coupling. So site energy is nothing but when an electron localized energy. That is when an electron is localized at particular energy. That corresponding energy is nothing but the site energy. Another one is electronic coupling means orbital overlapping between neighboring adjacent orbital. The interaction between orbital. So that is coupling strength between one orbital to next. For example, first molecule next molecule. So if you want to study the whole transport mean, we should look the home orbital. If you want to the electron mean, we should look the LOMO orbital of first molecule, next of LOMO orbital. So LOMO of first and LOMO of second molecule, how much interaction is there? That eigenvalue that is calculated from the computer from the type bending Hamiltonian. Here we are using Kohn-Shah method. So from that, so we can compute the site energy and electronic coupling and spatial overlap and so on. For that, we are using ADF's package. That means Amsterdam Density Functional Program package. Here in ADF, the commonly the slatter type orbital method. So slatted type means it's more accurate. We expect commonly it gives a more accurate result than Gaussian type orbital for this particular calculations. So in this way, next one is we should know aware of the reorganization energy. Reorganization means here, or we can say in other words, deformation potential. This one is calculated from the potential energy surface at neutral geometry and ionic geometry. Comparison of two ionic and neutral geometry. Using Nelson's 4-point method, one can calculate the reorganization energy. So it is purely depends on the geometric relaxation. That means when if you add the one positive charge or negative charge, that means electron or hole, how much minimum energy required to relax uh, that particular molecular geometry. That corresponding energy is nothing but reorganization energy. Next one is electronic structure calculation. For this basic calculation, we should start with the Gaussian package using here Gaussian and QChem for this one. For function, we are using hybrid method B3 lib. Basis set is 631 GT comma P. For orbital overlapping and site energy calculation using Becker-Perdue method using triple zeta double polarization GGA method. Here conversion criteria is 0.001 energy level cutoff is there. So here provision first we have to optimize the molecular geometry. Next construct the N monomer system, that is polymer system. That means dimer, trimer, tetramer, pentamer, hexamer, like that. So, so accordingly we have to calculate based on our property and stress system whether you want to go with dimer transport in dimer system or trimer system. Accordingly, you have to do calculations. That means construct the coordinates properly. So here, for in this way, here